Hello everyone, this is Dr. Webb. Welcome to the first video for multivariable calculus. So in this video we're going to be going over some real basic geometry in 2 and 3 dimensions. Much of this, perhaps all of this, is going to be review for you, but I wanted to go over some notation and conventions that we're going to be using throughout the term, just so we're all on the same page, speaking the same language. So let's start off real simple. Here is the xy plane. So the way that the term we're going to call this is we're going to call this R2. And so we have this fancy called Blackboard R with exponent 2 to it. So what the 2 in the exponent signifies is we're dealing in 2 dimensions. While this fancy R, this is how we represent the real numbers. So this is 2 dimensions in real numbers. And so really what we're talking about here is we're talking about points can be defined here in using 2 coordinates. Both of those coordinates are real numbers. Right? And so we're used to that being in the coordinates x and y. And so we have the x-axis going horizontally, we have the y-axis going vertically, and if we take some point up here, call the point x0, y0, well, that means that we went out on the x-axis, x0 away from 0, and then from there we went y0 up, and that gives us our point x0, y0. Now commonly in R2, in the xy plane, often we'll think about this broken up into 4 quadrants. And so we think about these quadrants counterclockwise. So the first quadrant is where both x and y are positive, so we call this quadrant 1. In the second quadrant, y is positive and x is negative, so we'll call that quadrant 2. In quadrant 3, both x and y are negative. And then in quadrant 4, x is positive and y is negative. So when we talk about the different quadrants, this is how we're numbering them. And then we're also going to be doing an awful lot this semester in 3 space. And so this is doing things in 3 dimensions. So here the 3 talks about, now we're talking about things with 3 coordinates, each of those coordinates being represented by a real number. Now the convention here in naming these axes is, and you can kind of see it somewhat here, we have our x-axis, our y-axis, and our z-axis. Now the way that this is traditionally drawn on, say, a chalkboard, which we're not going to have it all this term, but we will do our best, is we draw the axes out like this. The y and the z-axis, so the y-axis is going horizontally, the z-axis is going up and down, and so those 2 axes are lying sort of flat on the screen in front of you, and then shooting out towards you is the x-axis. So the y-axis and the z-axis are flat on the screen, and think about the x-axis is coming straight out at you. And then if we have some, let's use the nice axis that is already drawn up. Erase these cheap axes that I drew in. And so if we want to talk about some point on the, call it x0, y0, z0, well, the idea is that you go out x not far, and then you go out and across y0, and then z0 is how far you go up. Okay. And so that's how that's how we'll talk about points, and this is often how we'll draw them. So anytime you see me draw a quick axis for 3 space, the y-axis goes going horizontal, the z-axis is going up, the x-axis is coming towards you. So one thing that's a bit more interesting that we have in 3 space that we don't have in 2 space is we have more than one plane, right? And so we can talk about the xy plane. Let me erase this junk. So the xy plane is the plane that the x-axis and the y-axis lie on. And so this one, if you're thinking about this coming flat out, it's sort of like a tabletop coming flat out towards you from the screen. This is what's called the xy plane. Usually we don't write it like that. Usually we say xy hyphen plane. And then we can think about the plane that's on the screen, that's sort of the flat plane of the screen. Well, that's the plane that has the y and the z axes. And so this is in red here. This is the y-z plane. And then lastly, we have this vertical plane coming straight out from us that contains the x and the z axes. And so we're going to call this the xz plane. Okay. So what do points on these individual planes look like? Well, if you have some point on the xy plane, its coordinates are going to look like x naught, y naught, and then the z coordinate is always going to be 0. And in fact, if we wanted the equation for the xy plane, the equation would be all the points where z is equal to 0. On the yz plane, we pick some point on here. It's going to have a y coordinate and a z coordinate, but the x coordinate is going to be 0. Okay, and so this yz plane, these are all the points where x equals to 0. And similarly for the xz plane, we pick some point out here. It's going to have an x coordinate and a z coordinate. The y coordinate has to be 0. And so these are all the points where y is equal to 0. And given any point, let's call this ABC. Well, so the way that we drew this, so this is happening somewhere in 3 space. Well, we have this kind of going up above some point on the xy plane. Well, that point on xy plane would be A, B, 0. We're going to call this the projection onto the xy plane of ABC. So we're just focusing on, we're saying projection on the xy plane, we're just focusing in on the x and y coordinates and setting the z coordinate to be equal to 0. Similarly, we can talk about its projection onto the yz plane. And so we're going to force the x coordinate to be equal to 0. Call that 0BC. Let's get this correct. 0BC. And then last but not least, we can talk about the projection onto the xz plane. And so here it would be A0C. Okay, so for any point, we can talk about projections, and then, if we have curves, we can then talk about, since curves are just made up of a bunch of points, we can talk about the projections of each of those points. Okay, so whereas the XY plane is broken up into quadrants. If we do the same thing in terms of the axes, we actually get 8 different places, and so we're going to call them octants. Now we're not going to number these. I don't think anyone would really remember any numbering system that we did, but most times we're going to, at least in terms of drawing stuff, we're going to be focusing in on this sort of primary octant where everything is positive. And so this is going to be the primary octant. There are 7 other octants. At times we will be using them, but they don't have special names like quadrants do. Okay, one of the most important bits of geometry, and especially when we're doing things, we're trying to do calculus, is knowing exactly how to calculate distance. So let's start off in R2. And so you know well how to do distance in R2. So if we have 2 points, x0, y0, x1, y1, we draw a straight line between them. Let's call this one P0. Let's call this one P1. Well, the question is, how do we figure out this distance between the 2 points? What's the distance between P0 and P1? And the trick that we do is we use the Pythagorean theorem, break this up into a right triangle, where the base of this triangle is going to be just focusing in on the x coordinates. And so the length here is x1 minus x0. And then for the vertical side, this is focusing in on the y coordinates. Length here is going to be y1 minus y0. And then the Pythagorean theorem says, that this distance between the 2 points squared is going to equal, well, the length of the bottom, x1 minus x0 squared, plus the length of the vertical side, y1 minus y0 squared. And then if we want to solve for this distance by itself, we get distance between the 2 points is then just going to be the square root. And because we're squaring both of these quantities, anytime you square something, it's going to be non-negative. And so inside the square root, we have 2 non-negative things being added together, and so that's going to give us something non-negative, and so this always makes sense. So you don't have to worry about if x1 minus x0 is negative. Once we square it, that takes care of that. Okay. So this is distance in R2. Hopefully you're very familiar with this. Okay, what about doing distance in R3? So now we've got 3 coordinates, x0, y0, z0, call this p0, and then we've got some other point in R3. Let's call this x1, y1, z1. And let's call this point P1. And so the question here is, how do you find this distance between these 2 points in R3? Okay, so this is a little bit more difficult than in R2. But the idea is going to be basically the same, in that we're going to use the Pythagorean theorem, and we got to break this up into a right triangle. Now see, in this right triangle, the height here is just in terms of z. So this height here is talking about this height here is just going to be the difference between the z coordinates. So because it is going purely up, so it's going to be z1 minus z naught. But this length on the bottom, both the x and the y coordinates are changing. And so in fact, if we took this point right here, this point right here would be x1, y1, but we've made the height the same as for p naught, and so its height is z0. And so now, looking at these 2 points, they have the same z coordinate. And so all of this is occurring on a plane where only the x and the y coordinates are changing. The z coordinates are staying the same. Okay. And so we can break up this length right here into how is the, let's give myself some space, erase some of this junk. So this is our x naught, y naught, z naught. And this is our x naught, x1, y1, but at z naught. Okay, and so what we're going to do here is we can imagine it being, well, how much does the x change? And then how much does the y change? And so that's going to be another right angle there. And so this length right here is x1 minus x naught. That length right there is y1 minus y naught. And then this side that's now in green is the hypotenuse of that triangle. And its sides are x1 minus x naught and y1 minus y naught. And so this length here, let's call that L, using what we did for distance in R2, is going to be x1 minus x naught squared plus y1 minus y naught squared. Okay, so that gives us our length on the bottom. Our height is coming from z1 minus z naught. And so our total distance between the 2 points are going to be this lower hypotenuse squared plus, say that distance squared, plus z1 minus z naught, quantity squared. And then plugging in what we have for L, P0, P1 squared. L, if we square it, we cancel out that square root. And so we have x1 minus x naught squared plus y1 minus y naught squared plus z1 minus z naught squared. Okay. And so same thing we did before. If we want to get rid of the square roots, we can write this, or get rid of the square. On the left-hand side, we have the distance between the 2 points is going to be the square root of x1 minus x naught squared plus y1 minus y naught squared plus z1 minus z naught squared. Okay. And so you can see this follows the same pattern in R2. Just when we add in that extra coordinate, it also gets the difference between those, the z's gets stuck in, but you take the difference between the z's, you square it, and stick it in underneath the square root with the difference between the x coordinates and the y coordinates. And that's going to be how we do our distance in R3. This idea of, building another right triangle to get up to higher and higher dimension, this keeps going on. And so if we wanted to do this in R4 or R5 or R6, it would be the exact same idea. You'd have a square root, and then you take the difference between the coordinates, square each of those, add them together, then take the square root of the whole thing. And that's how you get distance in higher dimensions. So, one of the things that we'll see throughout the semester is, we're focusing in on R2 and R3 to a large degree, but that's because it's sort of what our brain can handle. But a lot of the ideas of what we're doing we can apply to higher and higher dimensions, 4, 5, 6, 100, a million, whatever. The difference is going to be that we can't really draw those dimensions well. We'll just be able to write down coordinates and play around with that. Okay, so now that we know how to do distance, we can talk about circles and their analogs in other dimensions. And so for a circle in R2, hopefully this is review. The idea is that you start with a point. Let's call that point AB. And then you pick a radius. Let's call that R. And then what the circle is, so the circle with radius R, centered at the point AB, is all the points, or the set of points, x, y, such that the distance between AB and XY is exactly R. And so now that we know the distance formula in R2, we can just write this out. And so we know that the distance is exactly R, so we can use the squared version. And so that distance squared is going to be the difference between the x-coordinate squared plus the distance between the y-coordinate squared. And that's going to give us our equation for the circle. Okay. Now there's one special circle that we're going to be using an awful lot, which is the unit circle. So the unit circle, this is centered at the origin. So centered at 0, 0, and it has radius 1. We are often going to be talking about the points on the unit circle. And so one of the ways that we're going to think about these points is if we draw a line out from the origin, we're going to be thinking about the angle. For us, it's always going to be, pretty much always going to be in radians. Up from the x-axis, we'll call that theta. And then the coordinates of that point right there are going to be cosine theta, sine theta, and this is corresponding to one of the favorite forms of the Pythagorean theorem, and that's that cosine squared plus sine squared is always equal to 1. And so the points on the unit circle, we can think about them in terms of this angle, theta, and the relationship between them. The x-coordinate is going to be the cosine of that angle. The y-coordinate is going to be the sine of that angle. That really is the definition of cosine and sine. And then we have this, since this is all on the circle centered at 0, 0 of radius 1, what that tells us is that cosine squared plus sine squared always has to equal 1. So if we want to do the same trick in R3, we don't get circles, we get what are called spheres. Hopefully you know what a sphere is. And so it's the same idea. So for a sphere, we're going to center it at some point, let's call it ABC, with radius r. Well, the sphere is the set of points x, y, and z. Whose distance from ABC is exactly r. And using our distance formula for 3 space, we can just pop this equation right out. We get r squared is equal to x minus a squared plus y minus b squared plus z minus c squared. And so that's the basic equation for a sphere in R3. Before I jump ahead, I want to talk about, at times we will talk about the unit sphere. And so the unit sphere is centered at 0, 0, 0 with radius 1. We don't have the nice sine-cosine relationship with the, well, there is sine-cosine relationships for the unit sphere, similar to the unit circle. It's just that there's more than one. And it kind of depends on how you want to pick your coordinate system. And so I'm going to leave talking about coordinate systems and different coordinate systems in R3. So right now this is being called what's called the rectangular coordinate system, because all the coordinates are straight. We'll leave talking about other coordinate systems for later on in the term. What I do want to talk a little bit about in R3 are what are called cylindrical surfaces. So, pretty much so far in math for the last however many years, you've been thinking a lot about, functions of the form y equals f of x, and what they look like on the xy plane. So what a cylindrical surface is that it's sort of the same idea of the stuff that you know. So if you have one coordinate, you have one variable in terms of the other. So in this equation here, y equals f of x, we have the y is dependent on what the x variable is. And so we can draw some curve, y equals f of x, on the xy plane. And so we can say, that is not a function. Let's make this at least somewhat accurate. So if I wanted to do y equals f of x, I'd have to draw it on this way. Oh, there's a much nicer one. And so this is y equals f of x on the xy plane. Well, in this equation, we haven't specified anything about the variable z. And so the way that we're going to turn this into a surface is we're then going to allow be and below this curve on the xy plane, we're going to allow all possible z values. So we're going to be going up and down. And so we kind of get this surface coming out, think about it kind of coming out vertically towards you, the xy plane. This is an example of what's called a cylindrical surface. So in a cylindrical surface, it's defined by an equation using only two variables. third variable can be anything. And the idea to get an idea of what these cylindrical surfaces look like is you draw the curve on the plane of those two variables that you know. So in this case, for this y equals f of x, we know, how to get y in terms of x. So this is defining a function on the xy plane, and then you go straight out in the other direction. So in this case, we went straight up in the z direction. So to close out this video, let's do one example of this. So let's sketch a graph of z equals y squared. Okay. And so this is in terms of, the equation here is in terms of y and z. And so let's write our nice coordinate system. Y and z. X is coming straight out towards us. Okay. So then on the YZ plane, this is going to look like a parabola, kind of going up. Like this. And then the x-coordinate can be anything. And so really you can think about this parabola getting shifted back and forth along the x-axis. And so there'd be sort of another branch coming out here, and then the surface then would be kind of joining this together between these. And so you can kind of think about it as being a parabola shooting straight out towards you and going back into the wall as well. So why do we call these cylindrical surfaces? Well, sort of a most basic form of this is if we take x squared plus y squared, say, equal to 1, so this is the unit circle. So this is all happening on the xy plane. And so there's sort of the unit circle on the xy plane. And then z then can be anything. So z is going up. What's the shape that you get from this? Well, you get a cylinder. And so this is sort of this is why this is called cylindrical surfaces, because cylinders can be made out of this. Okay, thank you for listening. Bye.